the rocket. And rocket is a very complex system. That's the reason we call it rocket science. It's a very, very complex system. Though it hardly works for about 18 minutes to 20 minutes in the space, but it's such a complex system. And now, see, rockets are made in these two places. One in the engine and another one is the rocket structure and the electronics, avionics, everything. And then coming to satellites, where the satellites are made? Yeah. So satellites, we make it in our center. Earlier it was called as ISRO Satellite Center, ISRO, like ISAC. Now we have recoined it, we have changed the name, like it is now called as UR Rao Satellite Center. Probably you will be knowing who's Professor UR Rao. He's a very, very eminent space scientist, world-renowned space scientist, Udupi Ramachandra Rao. So we have a center now there in Bangalore where we design the satellites. Now, like a rocket, there are two very important components satellites. One is the main bus, the structure. The other one is an engine, but engine is not, it's an optional for a satellite. Okay, engine is an optional thing. And the very important thing, a part of the satellite is a payload. So when we call a payload, what is a payload? Anyone?
Experimental instrument.
Pardon?
Experimental instrument for testing everything.
Yeah, not necessarily experimental. It can be operational. A payload. Yeah, a payload is an instrument, okay, which does the primary function. See, for example, if you are launching a satellite for communication purposes, so the payload should be a transponder. That means essentially a receiver and a transmitter combined together, it's called as a transponder. So a transponder is the payload for a communication satellite. Okay, if you are sending a satellite, if you want a satellite for Earth observation, imaging, so what should be the payload? Obviously a camera, a optical, or even a radio telescope. Okay, a radar. So now these payloads are made in a different center. Can you take a guess where these payloads are made for all the Indian satellites? We have a center in North India.
Pune?
North India. No.
Pune?
No. Gujarat. And there, to be very precise, it's in Ahmedabad. Okay, so this is called Space Application Center. So Space Application Center in Ahmedabad, all the payloads for Indian satellites, whether it is an optical payload or an electronic payload like radio payloads, all these payloads are made in a center called SAC, SCSC, Space Application Center. And they develop the payload, and these payloads will come to Bangalore, and those payloads will get integrated with the main bus spacecraft, and the satellite will be tested here in Bangalore. But except the payload, all the other systems are designed, developed in Bangalore. Now the satellites are ready here in Bangalore. The rocket structure, the main rocket, and the engines are ready in Trivandrum, Mahendragiri. Now, so we need to take the rocket into the space, isn't it? Along with the spacecraft. Now we need a
Launch pad.
yes, a spaceport, right? Like an airport. So any idea? I think already many of you gave the right. Sriharikota. So Sriharikota, we have a center called SDSC. It's named after. Yes. Yeah.
Why they selected this Sriharikota? Why not some other part?
Yeah. The main reason, the criteria for selecting the launch centers are mainly in the coastal area. Okay. Almost all the nations, they prefer the coastal area. But there are certain launch pads which are not, like for example China and Russia also. Okay, the Baikonur and all the other spaceport, it's not on the ocean, on the seashore. Okay, but the main reason is, in case if there is any failure or anything, so that the rocket will plunge into the sea. That is the main idea. And sir asked me, why specifically Sriharikota? Why not Trivandrum or Kanyakumari? Okay, so the main reason is, we always put the satellites in two major orbits.
Polar and
Yeah. You know what is a polar orbit?
Almost perpendicular to the equator.
Yeah, of course. Perpendicular to the orbit. So the name itself clearly implies that when you make the satellite to go over the poles, over the North Pole and South Pole, and we call this as a polar orbit. But there is another orbit,
Equatorial.
of course, over the equator, equatorial orbit, but at a very high altitude. You know, that is somewhere around 36,000 kilometers from the surface of the Earth, over the equator. And this orbit is called geostationary. You know what you mean by geostationary?
The satellite will stay at the same place. For example, if it's on India, it will stay.
Exactly. So when you put a satellite over the equator at about 36,000 kilometers orbit, and you see that the satellite takes about 24 hours to make one rotation. That is the one orbit. And we all know that Earth also takes 24 hours to make one rotation. So you are synchronizing with it. As you see now, this vehicle is going at around 40 kilometers speed. Another vehicle which is also passing at about 40 kilometers, there is no relative motion between these two vehicles, and the relative motion is almost like zero. We can talk to them. We can also even have a handshake, which we are not supposed to do, but it is something like that. So the Earth rotates on its axis and takes about 24 hours, and the satellites which we make to go over the equator also see that the orbital period is about 24 hours exactly. So it is synchronized with the rotational velocity of the Earth. So Earth takes 24 hours to make one rotation. The satellite also takes about 24 hours to go around. So it appears to be stationary, though it is not stationary there. No object in the space can be stationary. Okay, now just to give you an idea at what velocity this particular geostationary satellites or a spacecraft will be traveling at. Any idea? Any guess? Pardon?
Periphery
At
divided
what
by
speed this
17,500 miles per hour. That's yours.
now?
periphery divided by time 24 hour.
Yeah, the velocity, no, it will be much little lower. Okay, I'll just give you. It travels at around 3.2 kilometers per second. Every second, 3.2 kilometers. Just imagine. So 2 seconds, 3 seconds, 4 seconds, it would have traveled so much of distance. In spite of traveling that high velocity, okay, speed, still it appears to be stationary. So the classic good example, can you give me? That it is just to tell the geostationary orbits, the satellites are appearing to be stationary. Some example? The common sight we always see.
Moon.
What do we have on our terrace?
Moon.
You know,
Stars.
antennas, you know, the DTH antenna. So from where we get the signals? From which kind of a satellite? Geostationary satellite, and of course communication satellite. Okay. So now why these antennas are not moving?
So they're pointing at the satellite.
It is pointing at one particular direction, telling that there is something which is fixed there. So is that satellites are fixed there? No, it's moving around. It's going around. But it appears to be stationary because we are also traveling at the same velocity, rotating, right? So that is the reason the DTH antennas are always looking at one point. Now imagine if there is a relative motion between these two. If the satellites keep moving, like the vehicle starts moving like this and this, we may not be having a eye contact with them, isn't it? We have to move our head, eyes this way, that way. The same thing is going to happen if these two rotational velocities are not synchronized. Okay, so now imagine a spacecraft which is traveling at the velocity of 3.2 kilometers per second, the spacecraft which you cannot see with your naked eye, unaided eye, and we have to see that the satellites are precisely placed at that orbit and it maintains that velocity. And not only that, a satellite is something like a humanoid. Okay, you can just imagine like that. It's a electromechanical, chemical, everything is there in that. Okay, so electronics, mechanical, chemical, computers, everything is involved.